Students, now let us study about the pressure in liquids. Students, we know that matter occupies space. Matter has weight and it can exert pressure as well. The pressure of a body depends on the weight as well as on the surface area occupied by it. This has been proved in the previous sections. Let us study about liquid pressure in this section. The general concept of liquid is water, but there are many examples of liquid. It is a state of matter. Students, since matter occupies space and has weight, liquid also occupies space and has weight. A body which has weight can exert pressure. Therefore, liquids can also exert pressure. We know that pressure is given by pressure equals to force by area, or simply pressure is equal to mass into acceleration due to gravity by A, or the area, since force is equal to the product of mass and acceleration due to gravity. Or simply we can also write pressure is equal to density into volume into acceleration due to gravity divided by area. Since density is equal to mass by volume and mass is equal to the product of density and volume. So we write the relation as P equals D into V into G divided by A, where P stands for pressure, D stands for density, V stands for volume, and G stands for acceleration due to gravity, and finally A stands for area. Now, since volume is given by area into height, we write this equation as P is equal to D into A into H into G divided by A. Students, now the area in the numerator is cancelled by the area in denominator. Hence, P is equal to dHg, or the product of density, height, and acceleration due to gravity. Students, hence pressure exerted by the liquid is equal to the product of the density, depth of the liquid, and acceleration due to gravity. If the density of the liquid increases or depth increases, the pressure also increases. Now, let us look at some examples given here. The first example reads, what is the pressure exerted by water in the given figure? The density of the water is given as 1000 kg per meter cube, and the value of acceleration due to gravity is equal to 10 meter per second square. Now, let us solve for this. Students, we have been given the density of water, that is D, as equal to 1000 kg per meter cube, the depth of the liquid, denoted by H, as equal to 2 meter, the acceleration due to gravity, that is G, equals 10 meter per second square. Now we have to calculate the pressure, that is P. We have the relation pressure equals to depth into density into acceleration due to gravity. Now here we have the value of H, D as well as G. So substituting these values, we calculate the value of pressure. So we write P is equal to 2 into 1000 into 10, which equals 20,000 Newton per meter square. Hence, the pressure exerted by water in the given figure is 20,000 Newton per meter square. Students, now the problem given in the next example is, what is the pressure at 6 meter depth for a liquid that has a density equal to 800 kilogram per meter cube? Here is the solution. Students, we have been given the density, that is D, as equal to 800 kilogram per meter cube. The depth, denoted by h, is equal to 6 meter, and acceleration due to gravity, that is g, equals 10 meter per second square. Now let us calculate the pressure. Students, we have the relation pressure is equal to the product of the depth, density, and acceleration due to gravity. We have the values, so let us calculate pressure. We write P is equal to 6 into 800 into 10, which gives us 48,000 Newton per meter square, or 48,000 Pascal. Therefore, the pressure at 6 meter depth for a liquid that has a density equal to 800 kgs per meter cube is 48,000 pascals. Now, let us look at some more examples. This one reads, the length, breadth, and height of a water tank are 3 meter, 2 meter, and 2 meter respectively. If half of it is filled with water, what pressure is exerted at its bottom? The density of water is given as 1000 kgs per meter cube, and the value of acceleration due to gravity is equal to 10 meter per second square. Now look at the solution. Students, first of all, we have been given the density, that is D, as equal to 1000 kg per meter cube, the depth, that is h, is equal to 1 meter, and acceleration due to gravity, that is g, as equal to 10 meter per second square. Now we have to calculate the pressure. We have pressure is equal to the product of depth, density, and acceleration due to gravity. Students, we have all these values, that is depth, density, and gravity. So let us calculate pressure. So we write P is equal to 1 into 1000 into 10, which gives us 10,000 Newton per meter square. Hence, the pressure is 10,000 Pascal. Therefore, the pressure exerted at its bottom is 10,000 Pascal. In the other example, the question is, a drum is filled with liquid. The height of the liquid in the drum is 2 meter and its pressure is 500 Newton per meter square. What is the density of this liquid? Now here is the solution. Students, we have been given here the pressure P as equal to 500 Newton per meter square, the height or h as equal to 2 meter, and acceleration due to gravity or g as equal to 10 meter per second square. Now here we have to calculate the density, that is D. Again, we use the same relation, that is pressure is equal to h into D into g. Students, we have the values for P, h, and g. So substituting these values, we can calculate the density. So we write the equation as D is equal to P by h into g. Now let us substitute the values and we write 500 divided by 2 into 10, which gives us 25 kilogram per meter cube. Therefore, the density of the liquid is equal to 25 kilogram per meter cube. Now look at this activity. It's about liquids exert pressure. Students, take a small tube, open on both sides. Fix a rubber membrane at one end of the tube and put some water in it. You notice that the rubber membrane begins to extend. The extension in the rubber membrane is due to the liquid above it. Liquids have their own characteristics. The characteristics of liquid can be summarized in the points below. The pressure of liquid at a point within it is directly proportional to the depth of the point from the free surface of the liquid or the height of the liquid column above the point. For verification, pressure is directly proportional to height. Students, take water in a cylinder or a long tin can, having 3 holes fitted with stopcocks.
When the stopcocks are open, water emerges out of the holes as shown in the figure 1. Now, water from hole 1 emerges with the least force, whereas water from hole emerges with the greatest force. It means pressure at hole 3 is more than at hole 1 and 2. Moreover, the pressure acts on the sides of the vessel, which is called lateral pressure. This shows that pressure at a point increases with height of the liquid above the point. Students, the pressure at a point is directly proportional to the density of the liquid. That is, P is directly proportional to D. As the density of the liquid increases, the pressure of the liquid also increases. The pressure and thrust of a liquid at rest are always perpendicular to the surface in contact with it. The pressure at any point within the liquid is the same in all directions. That is, the liquid exerts pressure equally in all directions. The pressure at a point within the liquid does not depend on the volume of the liquid in the vessel, but it depends only on the height of the liquid above the point. The pressure at a point is independent of the shape of the vessel.
Students, look at the statement. It says, liquids transmit pressure equally in all directions. This law is also called Pascal's law. Now look at the verification. For the statement, liquids transmit pressure equally in all directions. Students, take a hollow rubber ball or polythene bag. Make a number of small pinholes. Now fill the ball with water and press it. Water comes out of all the pinholes simultaneously. This shows that the increase in pressure on the liquid at some point is communicated equally in all directions. The other statement is, liquid maintains its level. Let us look at the verifications for this statement. First, verification 1. Students, take a glass and fill it with water. The water level is parallel to the ground. Now tilt the glass and you will see that the water level is still parallel to the ground. This proves that liquid maintains its level. Now look at verification 2. For this, take a U-shaped tube and fill it with water. You can see that liquid level is same in both the legs of the tube. This also proves that the liquid maintains its level. Verification 3 says, in the given figure, you have been given a glass vessel which has different structures attached. Look at it properly. Now, as you go on filling water in this kind of vessel, you will notice that the liquid level in each structure is the same.